Actually, the universe has no outside. Some might argue, since it's expanding, it must be getting larger. But it's not matter expanding into some larger space, but space itself creating new space. So in the next few dozen minutes, we will track this concept. From Hubble's redshift, to the microwave background in TV static. From a beach ball-sized early universe, to the time Einstein called the cosmological constant a mistake. Finally, you might discover that what we call the outside is perhaps just an unreachable illusion. To make this abstract concept easier to understand, let's use a simple analogy. Imagine inflating a balloon in your living room. Air is blown in, the rubber stretches, the balloon takes up more space. It gets bigger because there's room to grow. Your living room is its outside. Because of this, we naturally compare cosmic expansion to the same thing. Space seems to expand into a larger cosmic room. Since it's growing, there should be a boundary and an end. This idea seems logical, but it hits a cognitive trap. Physics tells us the universe doesn't work that way. When space expands, it's not pushing into some exterior, because there is no outside, no container or empty void to fill. While the universe gets larger, it also generates its own space. A better analogy is, if you want to draw a circle larger than the paper, you don't get a bigger piece of paper, but let the paper itself grow to accommodate that line. This sounds awkward, because in our daily experience, expansion must grow into somewhere. Plants grow into the air, cities expand, ice spreads on water. So, we subconsciously use inner and outer. But if you are both the paper and the drawing, the concept of outside loses meaning. So the question isn't where the universe goes, but how we know space itself is growing. The answer comes from the most distant starlight. By observing distant galaxies, scientists realized this counterintuitive fact. Hubble found that the further a galaxy is, the faster it moves away. At first glance, this suggests we are at the center of a cosmic explosion, as if everything is flying away from here. But the truly bizarre thing is, galaxies aren't moving through space, but the space between them is being stretched. A reverse balloon analogy is more intuitive. Think of galaxies as dots on a balloon. When the balloon inflates, the distance between dots increases, but the dots aren't crawling on the surface. The surface itself is expanding. Every dot sees others moving away, and no single dot is the center. Take this 2D surface and replace it with our 3D space, we get the key conclusion: the universe isn't expanding into an outside place. Because there is no outside for it to enter. It creates its own stage as it grows. This boggles the audience's mind, and baffled the geniuses of that time too. Even Einstein was reluctant to accept it. But the thing is, this seemingly impossible expansion is happening now at unimaginable speed. Next, we must answer a tough question: how do we know all this isn't just a pretty metaphor? The clue lies in light's stretching journey. When a distant galaxy emits light, its wavelength is fixed. Whether it's blue light, red light, or infrared, it has its own fingerprint. But when this light travels through ever-expanding space, the path beneath it gets longer. Imagine walking on a moving walkway that slowly stretches. Your stride hasn't changed, but the surface is quietly elongated. By the time you reach the end, the distance exceeds your step count. For light, the result isn't a longer journey, but a stretched wavelength. So blue light from afar reaches us as red light. The key point is, this isn't like an ambulance passing by, the Doppler effect from speed. It's space being stretched during the journey, pushing peaks and troughs further apart. This is cosmological redshift. It directly proves the growth of space, independent of object movement. More intuitively, a mechanism that stretches the ruler of your 3D world is shifting ancient light to a new range. Here's another mind-blowing set of numbers. Light from the most distant galaxy has been stretched nearly 40 times. Intense ultraviolet pulled to faint infrared. During its multi-billion-year journey, the universe expanded nearly 40 times. And so, that galaxy you see in the telescope is tiny and dim. But when light left it, the universe was much smaller than today. It was closer to the future Milky Way. Clearly, space didn't just grow slightly, it's a continuous, grand stretching. More importantly, this stretching isn't happening in some remote corner, but everywhere. Right now, space in this room is expanding. The space between your eyes and the screen is also trying to pull apart. You don't feel it, because electromagnetic forces bind matter together firmly. The force of expansion is negligible at this scale. Only in the gaps between galaxies, where atomic glue is missing, can expansion act freely, carrying them further and further away. It's like love and dough, carrying raisins apart. Raisins don't actively swim in dough, the dough itself is growing. So when you ask where the universe expands to, it's like asking where the dough is going. Don't forget, you are part of the dough. But since space is stretching everywhere, How far can we actually see? To put it bluntly, we live in an invisible cosmic prison. Its walls are built by time itself. Looking at the night sky, you'd think the whole universe is before you. But facts will overturn that perception. What you can see is likely less than 4% of the real universe. The reason is simple, yet cruel: light speed is finite. The universe's lifespan is finite. The further you look, the further back in time you go. The sun is seen as it was 8 minutes ago. Alpha Centauri as it was 4 years ago. Andromeda as it was 2.5 million years ago. The universe is about 13.8 billion years old. This means the oldest light has traveled at most 13.8 billion years. Galaxies beyond this duration effectively don't exist to you, because their light is still on its way. But don't forget, space has been expanding during this time. Those distant galaxies, when emitting the light we receive today, were much closer to us. When this ancient light finally arrives, expansion has carried them 46 billion light-years away. So our observable universe is a bubble with a 46 billion light-year radius. Beyond it are more galaxies and stars, perhaps even another you reading these words. You can't see them not because they aren't there, but because light hasn't arrived yet. Everything outside the bubble falls into the unobservable universe. It's not a physical barrier, but the laws of physics setting a limit. Think of it like a thick fog that limits your vision to a set distance in any direction. You know there's a world beyond the fog, but you can't see through it. Furthermore, if the universe is near infinite, your tiny observable bubble, in the grand scale of the whole, is almost a perfect zero. To understand where this time wall is, look back at the oldest light. Today, the oldest light in the universe is rushing toward you at 600 million miles per hour. It's older than the solar system, older than the Milky Way. Its journey began when the universe was only 380,000 years old. Then, the universe was hot plasma, so hot that atoms couldn't form. No photon could travel more than inches before being caught by charged particles. As the universe continued to expand and cooled down enough, protons and electrons first combined. The fog finally dissipated, the universe became transparent, and light could travel freely. This is the recombination stage. The first batch of escaping photons is what we observe today as a cosmic microwave background. Radiation is everywhere, filling every cubic inch of space. Even on old TVs between channels, the snow on the screen. About 1% of that noise comes from this distant light. More importantly, it marks the edge of all we can see. You can never see through this horizon, because the early universe was as opaque as the sun's interior. Events before 380,000 years are forever hidden. To put it simply, the cosmic microwave background is that earliest brick wall. It defines the limit of observation. On the surface, this wall is still receding. In another second, a beam of light traveling for 131.8 billion years plus one more second reaches us. Thus, the radius of the observable universe gains 1 light second every second, which is about 300,000 kilometers of new space entering our view. By the day, we can see about 16 billion miles of more universe every day. But on second thought, there's another layer. Though the screen is getting bigger, the light sources are being carried away by expansion. For example, a galaxy that emitted photons 13 billion years ago now might have been pulled 30 billion light years away. We see it as it was then, not its current position. This sense of the film zooming in while the actors recede is daily life in cosmological observation. Even so, the microwave background still tells us a crucial fact: the early universe was almost perfectly smooth. Temperature fluctuations were only a few millionths. Yet these tiny ripples eventually birthed today's galaxies and us. Now, let's look at what might be outside the bubble. Based on our measurements of the CMB, the universe is roughly uniform at the largest scale. This means no matter where you start, the composition and ratios are similar. Like a bowl of perfectly mixed cake batter, every spoonful contains the same ingredients. By extension, if our observable universe holds about 2 trillion galaxies, then outside this world, in another region of the same size, it likely holds about 2 trillion galaxies too. And so it goes for regions beyond. This pattern extends piece by piece. More excitingly, if space is near infinite in scale and remains uniform, then in any given volume, all possible arrangements of matter will repeat. Sounds like metaphysics, but the conclusion is mathematical. Finite microscopic arrangements plus infinite volume, repetition becomes inevitable. At this point, the metaphor of paper and drawing as one aligns with the observational evidence. We don't need an outside to hold the universe. What we really need to track is how this paper keeps stretching, and how, as it approaches infinite scale, it fills in every possibility. Since on an infinite scale, it could fill in every possibility, then comes the most jarring conclusion: repetition is unavoidable. So consider a deck of cards. If you shuffle infinitely many times, the exact same sequence will eventually reappear. The universe works similarly, but with atoms and their arrangements. So in an extremely distant place, there must exist another you reading this text. This isn't a metaphor, but a literal deduction. Because in regions where light can never reach us, quantum mechanics has arranged matter in every possible way, including the one identical to your current state. So some yous will stop reading now, some yous were never born, and some live in a version of Earth with a completely different history. Mathematics even gives a sense of scale. These copies are about 1 followed by 115 zeros in meters away. A number so large that if written out, the length of the string alone would exceed the observable universe. But if space is truly infinite, such a distance is still finite. So somewhere, another you just realized this fact. A bit further, another you realizes the previous you also just realized it. However, all of this rests on one premise, that the world outside is similar to our side. What if it's not? Recent observations suggest our part of the universe may be sparse, like a cosmic void with density lower than the average. If that's the case, then crossing the observable boundary might reveal more crowded space, more galaxies, more black holes, more intense activity. Or perhaps the opposite, a void of almost nothingness. Bolder theories push back to the first instant. A brief, frantic cosmic explosion might have torn the whole into distinct pocket universes. They might have different physical constants, different particle spectra, even following alien physics laws, rendering our textbooks useless. And in our realm, things seem normal only because we happen to live in this specific pocket's recipe. But there's a deeper point that needs addressing. What if the universe isn't infinite? An expanding infinite universe brings a clever paradox. How do you make infinity bigger? The math says you can't. Infinity plus any number is still infinity. Times 2 is still infinity. You can't add more to something that already contains everything. Yet observations clearly show space is stretching everywhere. To resolve this conflict, the key is to stop seeing expansion as becoming more infinite. It's about the scale factor growing. Imagine infinite grid paper, 1 inch per square. Now stretch it to 2 inches per square. The paper is still infinite, the squares are still countless, but all distances have doubled. This is the essence of expansion. It's not adding infinity to infinity, but stretching the scale of the fabric, making all distances grow proportionally. So a galaxy 100 million light-years away, when the universe was half this size, was only 50 million light-years away. Then the deduction continues. If the universe is infinite now, then at the moment of the Big Bang, it must have also been infinite. The Big Bang isn't fireworks exploding matter from a single point, but more like infinite space expanding everywhere simultaneously and filled with energy. In other words, the Big Bang happened everywhere in infinite space. It has no center, no boundary, no outside. Any location can claim to be the center, because from any vantage point, the expansion looks the same. This perspective, on one hand, explains why in every direction we see almost the same universe. It also explains why we find no edge or center. On the other hand, it also raises new questions. If the universe holds infinite matter, why isn't there infinite density? The answer lies in the definition. Density is total mass over volume. Even if both approach infinity, as long as they grow at the same rate, the ratio remains finite. So the universe can fit infinite matter into infinite space, while maintaining finite density, roughly a few hydrogen atoms per m superscript 3. Here, the paradox gets personal. In a truly infinite universe, any event following physical laws will happen infinitely many times. It's not just another you repeating, but every version of every story. Tragedy and triumph, beauty and cruelty, play out somewhere. If this is unsettling, consider a finite universe instead. A universe with an end begs the question, what's beyond the edge? Can space truly have an end? If you try to cross this boundary, what happens? These questions lead scientists to favor a vast or near-infinite model. Though hard to visualize, it at least avoids the question of what lies beyond the edge. With the latest CMB measurements, we face either an infinite universe or one so large its curvature is undetectable, a near-flat universe. The simplest explanation is that space extends infinitely. So the expansion we see now isn't like adding a room to an existing house, but more like stretching an infinite fabric. What force drives this constant stretching of the fabric? To be blunt, the universe is expanding at a rate that would make any factory jealous, from the near-nothingness of quantum vacuum, producing new space. A rough calculation, every second, the volume of the observable universe would increase by about 11 followed by 78 zeros, in cubic meters. This number is so large that even if you counted one every second, the time required would far exceed the age of the universe. Even if you multiplied this time by itself billions of times, it would still not be enough. But a quantum vacuum isn't nothing, it's a boiling pot of never-ending foam. virtual particles constantly appear and annihilate in a split second. This is quantum fluctuation. It gives every point in space its own energy. What's truly counterintuitive is that this vacuum energy manifests through gravity. Unlike matter's gravity, which pulls things together, vacuum energy creates repulsion. It pushes space outward. The more space there is, the more vacuum energy exists. The more vacuum energy there is, the faster it expands. The faster it expands, the more new space is created. Turn this feedback loop to the maximum, and you get a runaway inflation. In the initial, infinitesimal moment, this process worked at a frantic pace. The rate at which space expanded exceeded the speed of light traveling through it. This isn't about anything moving faster than light, but rather the treadmill itself accelerating. Light on the treadmill cannot outrun the treadmill. During that time, a region smaller than a proton could be stretched in an unimaginably short interval to nearly the size of a basketball. It sounds like science fiction, but the ledger of quantum mechanics demands it. As long as you can return it fast enough, you can borrow energy from the vacuum. During the inflation phase, the universe borrowed a massive amount of energy to start producing space, then used expansion itself to settle the debt. It's like borrowing money to buy a printing press and using the printed cash to pay back the loan. The problem was, this mechanism worked too well. It only needed to create enough space to solve a few cosmological puzzles, but it didn't stop immediately. Instead, it over-delivered, producing a territory far larger than needed. So our entire observable universe is just a tiny patch on this giant fabric of explosive growth. Imagine blowing up a balloon to the size of Earth. What we can currently see is just a point the size of a needle tip. What's even more intriguing is that, though the early explosion has stopped, today's expansion still continues. But the rhythm has shifted to a new player. Dark energy, making up about 68% of the universe, behaves in a way almost identical to vacuum energy. It fills space uniformly and provides repulsive gravity, causing expansion to accelerate. As the volume grows, new dark energy appears to fill the new space. It sounds like it's creating energy out of thin air, which seems to clash with energy conservation. The key to resolving this is in the gravity ledger. Gravitational potential energy is negative. As space stretches apart, the gravitational binding energy between matter decreases. This more negative energy can offset the positive energy of new dark energy. The result is a universe that generates space while balancing the total ledger near zero. According to the script, expansion will continue for a very long time, far beyond the scales of human imagination. Every moment, new space is born, new dark energy appears, and the stretching of the universe accelerates. The reason the universe grows is not to occupy some external place, but because the expansion itself is creating its own stage. But even with such grandeur, all this still needs evidence to be solid. Where should we look for it? Clues aren't in distant myths, but hidden in very humble places. When you take an old television and switch between channels, in that static noise, a small portion comes from the universe's first light. The answer lies within that static. In 1964 at Bell Labs, Penzias and Wilson tried their best to eliminate the persistent hiss in their antenna. They changed directions, calibrated equipment, and even cleaned out the bird droppings. But the noise wouldn't leave. It turned out it wasn't a malfunction, but the echo of creation. They had stumbled upon the cosmic microwave background radiation, the afterglow of the Big Bang. Because space continued to expand, this ancient light was stretched and cooled. Today it's only about 2.7 K above absolute zero. For this reason, this discovery won the Peer Nobel Prize and provided the most direct evidence that the universe is expanding. More importantly, this background light doesn't just exist, its spectrum bears the fingerprints of inflation. Visible light once at 3000 degrees Celsius, was stretched with space, shifting first into infrared, then into microwaves, and finally extending into radio waves. At the same time, the entire sky's brightness is as flat as a mirror, uniform to within a few parts in 100,000. This matches the prediction of inflation. Without a rapid stretch early on to smooth out irregularities, we should see massive temperature differences now. But that is not the case. So the question moved a step further: where did those tiny remaining ripples come from? The answer lies at the quantum level. Inflation took subatomic quantum fluctuations and pulled them to cosmic scales. These faint energy fluctuations became the seeds of galaxies and stars. In other words, your ability to read these words is because quantum uncertainty was magnified by the universe into the macro world. Next, the evidence was turned into maps. Through the Cope and Planck satellites, humanity mapped these temperature fluctuations in great detail. The result showed the angular distribution perfectly matched the theoretical curve of inflation. Based on these ancient microwaves, we can not only see but also measure the universe. Geometrically, space is nearly flat within measurement precision. In terms of composition, matter is only about 5%. Dynamically, expansion rate and cosmic age can be narrowed down to a very tight range. Even more intuitively, the data gives us a staggering sense of scale. Today's entire observable universe was once compressed into a volume the size of a beach ball. Compression here isn't stuffing things into a box, but the compression of space itself. That beach ball wasn't a container for the universe, it was the universe itself at the time. There was no outside, and no surroundings. Only that compressed pocket of space-time. It then began expanding and cooling to create the starry sky we see today. So where did the energy to stretch space-time come from? To find the answer, scientists looked toward a more stable celestial phenomenon. In 1998, two teams used Type Ia supernovae as standard candles. They wanted to measure how gravity should be slowing the expansion down. The idea was simple: compare the actual brightness of these supernovae to their standard brightness. Combined with Redshift, they could calculate exactly how far they were. But once mapped, the conclusion was completely reversed. Distant supernovae were dimmer than expected, meaning they were farther than the standard model suggested. In other words, the space light encountered on its journey was stretched more than we thought. The universe wasn't being braked, it was accelerating. This discovery also won a Nobel Prize and introduced us to a new player. This player is dark energy. It now accounts for about 68% of the universe. Much more than all ordinary matter combined. It dominates the big picture more than dark matter. Its strangeness is that it neither clumps nor dilutes. Matter thins as volume increases, but dark energy density stays constant as space expands. So the larger the universe, the stronger its total influence becomes. Early on, matter and radiation ruled. Dark energy was just the background. As matter was stretched thinner and thinner, dark energy's repulsive effect began to surface. It became dominant about 5 billion years ago. Since then, the universe entered an era of acceleration. Projecting this trend forward, more and more distant galaxies will move away at speeds faster than light can chase. Eventually, they will fall out of observable range forever. But what is this invisible force? The leading candidate is vacuum energy, the ground state fluctuations of quantum fields within what seems like empty space. According to simple quantum field theory estimates, the vacuum should be packed with immense energy. But compared to observations, it is off by 120 orders of magnitude. This is likely the worst prediction in physics history. So, either we're missing a key puzzle piece of the quantum world, or nature has some mechanism to cancel out almost all vacuum energy, leaving only the tiny bit needed for acceleration. Beyond this, some propose that dark energy is a new field permeating the universe. Others suggest we should simply rewrite the laws of gravity on a cosmic scale. Whichever path we take, the current situation leads to one conclusion: our ignorance of it is similar to ancient humans looking up at lightning. But it indeed continues to shape the fate of the universe. Speaking of the universe's fate, we must zoom back to an even earlier moment. Many people will ask, if the speed of expansion is faster than light, what would happen? The answer doesn't contradict the principle that no object can exceed light speed, because it's not an object that's moving fast, but the scale of space itself. In the split second after the Big Bang, the universe entered the so-called inflation period. The distance between any 2 points doubled and doubled again in an incredibly short time, so fast that even light couldn't keep up. To think about it intuitively, imagine two ants standing on a rapidly inflating balloon. No matter how they crawl, they will only drift further and further apart. In terms of magnitude, inflation expanded the universe's scale at least 1 followed by 26 zeros. And all of this happened in only about 1 second's 100 millionth of a 10,000th of a second. For comparison, light only travels 30 centimeters in a nanosecond. What drove this frantic stretching was a quantum field called the INFL-Aton field. Unlike many fields with zero ground state energy, it was trapped in a high-energy false vacuum. Like a pool of water held high up, it could, in a short time, continuously pump energy into space. The terror of exponential growth lies in being inconspicuous in the early stages, only to surge violently later on. It not only smoothed out early fluctuations, making the sky look almost uniform, but also stretched the universe's curvature to near flatness, and amplified tiny quantum fluctuations into the seeds of all future structures. Your galaxy, your stars, even the atoms in your body, can all be traced back to the random fluctuations of that moment. But immediately after, a more unsettling question arises. If inflation really happened at the start, why did it only happen once? The kind of quantum field that drove the initial inflation likely still lurks behind the scenes today. As long as conditions are right, it would trigger a new round of exponential stretching. It could start a new Big Bang at any time and in any place. A bubble would form there, expanding outward at near light speed. Everything in its path would be rewritten. Inside the bubble, things would operate under a completely new set of physics. Our atoms would be dismantled, and the laws we know would fail instantly. And worst of all, we wouldn't receive any warning. But for inflation theory, this isn't even the most shocking inference. It's even more likely that our universe is just one bubble in an infinite sea of bubbles. At this moment, as you read these words, countless other universes might be born elsewhere. Each carries different natural constants, different particle families, and even different physical grammars. This sounds like science fiction, but it's actually a logical extension of inflation theory. If it happened once, quantum fluctuations would make it play out repeatedly on a grander stage. Thus, bubble universes are blown out one after another, each first inflating and then cooling, perhaps even nurturing their own galaxies and planets. Our universe is just one of them. In other bubbles, gravity might be stronger, where stars collapse into black holes as soon as they light up. Gravity might be weaker, where matter can never coalesce. Some bubbles have no electromagnetic force, making chemical reactions impossible. Other bubbles stay in an inflationary state, never cooling enough to form atoms. Most bubbles are too barren to be habitable. But in a truly infinite sea of bubbles, even the most improbable combination will appear in some corner. Thus, the anthropic principle finds a new explanation. The reason we find ourselves in a seemingly fine-tuned universe isn't that the universe was custom-made for us, but because only such a universe can nurture observers. In other words, we can see it because it allows us to exist. The next question isn't just physics, it also falls into philosophy. If there truly are infinite universes, then every possible experience will play out somewhere. Choices you didn't make will be completed by you in another bubble. Tragedies you avoided will fall upon another version of you. Your unfulfilled dreams will bloom in another branch of reality. In this way, uniqueness is diluted to being almost meaningless. The weight of a choice is also shared across countless parallel scripts. More troublesome is testability. By definition, other bubbles are outside our world. They send no light and leave no gravitational traces. We can neither directly prove their existence nor measure their properties. Because of this, many scientists are reserved about the multiverse. If it's not verifiable, it can't be called science in the strict sense. But on the other hand, the mathematical derivation of inflation strongly points toward eternal inflation and a bubble relay process. The same set of successful equations explaining the early universe's expansion also naturally suggests the conclusion of continuous expansion in a larger space, constantly forming bubbles. To complement this, the subtle statistical patterns on the cosmic microwave background highly coincide with inflationary predictions. While this doesn't directly prove the existence of other bubbles, it gives us more confidence that we might be living within the best evidence supporting the multiverse. Up to this point, you might still think of these as bubbles in 3 dimensions. But the latest physical attempts remind us that reality might be even stranger. What if inflation is happening in directions we can't perceive? String theory requires space to have 9 dimensions. Besides the 3 dimensions we know, there are 6 tightly curled, tiny dimensions. Hidden right here and now, so small that even particles can't detect them. We are likely like an ant walking on a garden hose. Only able to move back and forth along the hose, we mistakenly think the world has only 1 dimension. If these extra dimensions truly exist, they might expand along with 3-dimensional space. In that case, the question of where the universe expands has another answer. Our 3D space might be a membrane stretching into a higher dimensional hyperspace. The accelerated expansion we observe might be this membrane deforming within a larger dimension. Older brain world models even suggest that all particles and forces except gravity are trapped within this 3D membrane. Only gravity can leak into extra dimensions, which explains why it appears exceptionally weak. If there are other membranes parallel to ours in high dimensions, they might be in directions we can't see, right within reach, or even occasionally colliding. Some models simply explain the Big Bang as a collision between 2 membranes. The cosmic microwave background might be the afterglow left by that impact. According to this vision, over vast time scales, membranes might meet again and again. Each time is like pressing a restart button, starting a new cosmic evolution in our 3-dimensional space. There are even stranger speculations. While our familiar 3D space seems static, the extra dimensions themselves might be inflating. Or some dimensions are growing larger while others are shrinking. Thus, the overall volume might not change, but our 3D slice appears to be widening. These are all still hypotheses for now, as we cannot directly touch extra dimensions. The Large Hadron Collider is currently searching for signs of particles vanishing into hyperspace. But so far, no conclusive evidence has been captured. This might mean extra dimensions don't exist, or it could mean they are even more compact than we imagined. Even so, the mathematics of string theory still suggests that extra dimensions are likely an indispensable missing piece of the reality puzzle. Stepping back, even without those hidden directions, the shape of 3D space itself is enough to rewrite what expanding to where means. General relativity allows for 3 geometries, flat like an infinite plane, positive curvature like a sphere, and negative curvature like a saddle. Observations show our universe is either flat or so close to flat that it's hard to measure. But flat doesn't equal infinite. A sheet of paper is flat, but you can roll it into a cylinder, or glue the edges to make a torus. It remains locally flat, yet the whole can be closed and finite. If space is indeed self-closing in some way, then expansion simply increases the size of this closed structure. It isn't entering some external warehouse, but growing into a larger version of itself. Following this line of closed geometry, it would even leave observable traces. In a torus-shaped universe, light can travel around and return to the origin. We might then see duplicates of the same distant galaxy in different directions. In the cosmic microwave background, there should also appear repeated patterns overlaid after light has circled multiple times. Astronomers once tried to find markers of closed space on the cosmic map, but have yet to find any decent evidence. This could mean 2 things. Either, the universe is much larger than we can observe, or, at least within the scales we can currently detect, this self-closing structure simply doesn't exist. In other words, the universe might really be like a donut. It's just that this donut is so big, light hasn't had time to circle it yet. If we step back further from our spatial view, we see that space and time are actually one. 4-dimensional spacetime. The question of shape thus becomes more complex. Expansion doesn't just pull space apart, it also changes the relationship between space and time. In the early universe, everything was extremely compressed. The flow of time was completely different then. Simultaneity, as a concept, loses its unified meaning over vast distances. As space is stretched, time is stretched as well. Consequently, a scene emerges that seems to defy common sense. Some distant galaxies seem to recede faster than light. But they aren't racing through space. It's space itself carrying them away, while stretching out the scale of time. To those galaxies, they are almost stationary. It's just the rulers and clocks between us that are changing all along. Relativity tells us that from any position in the universe, the picture of expansion looks the same. Every observer feels they are at the center, with everything else moving away. No one has a privileged frame of reference, and there is no true outside vantage point. More importantly, this stretching isn't an abstract concept, it can be directly measured. For instance, in a nearby galaxy, a supernova cycle from bright to dim might only take 3 weeks. But if that same supernova erupted in a faster receding, more distant galaxy, this process, in our eyes, would appear stretched out like slow motion. The reason is simple. The light-carrying information of the event was stretched during its journey. Not only was the wavelength lengthened, but the interval between light pulses was too. So, we are seeing a version where time has been slowed down. To use an intuitive figure, light from galaxies near the observable edge has a redshift factor of about 10. This means their events, to us, appear 10 times slower than local ones. This also explains why the age of the universe actually carries a subjective tint. From our perspective, it is about 13.8 billion years. But if you stood on those receding galaxies, looking back at us, this space would look much younger. In other words, the early universe was compact in space, and compact in time as well. Many evolutions that today take billions of years back then might have occurred on much faster scales. The first stars, the first galaxies, the first black holes, all were born in that kind of rhythm. Furthermore, expansion shatters our intuition of simultaneity. Two events you think happen at once, to a distant observer, might not be synchronous at all. There is no unified now in the universe, only individual, local moments. And as dark energy's influence grows, this time-stretching effect will amplify. Future observers looking afar will see even more extreme time delays, until events seem almost frozen. This leads to the universe's future script. Based on current understanding, expansion will thin out matter and energy. Inevitably, the universe will reach heat death. Temperature differences will flatten out, and the capacity to do work will dry up. The entire world will be a uniform void near absolute zero. The rough timeline is as follows: in about 100 billion years, the last stars will exhaust their fuel. No new stars will ever be born. The universe enters the degenerate era, dominated by frozen stellar remnants. By roughly 10 to the 34th power years, protons may start to decay. The building blocks of atoms will crumble. The universe will hold only electrons, positrons, and photons, drifting in an ever-expanding void. Pushing the scale even further, in about 10 to the 100th power years, black holes will be the sole energy source. They will slowly evaporate via Hawking radiation. Supermassive black holes might last until 10 to 100 power years, when the very last black hole dissipates into faint radiation, the universe reaches maximum entropy. No chemical reactions, no possible computation, and no place for life. Unless the nature of dark energy changes fundamentally in the future, accelerated expansion will drive us toward this icy end. In the nearer future, the impact is still far from gentle. As space-time is pulled apart faster, distant galaxies will slip out of our observable range. They won't be destroyed, but they will recede so quickly that their light will never reach us again. Later, even the cosmic background radiation will be stretched beyond detection. Astronomers of that era will only see a lonely local group, surrounded by endless void. Key evidence of the Big Bang will be gone. By comparison, the Big Rip scenario only occurs in extreme hypotheses. If dark energy keeps intensifying, it will overpower all known forces. From gravity and electromagnetism to the strong force, everything will be torn apart. The universe will disintegrate from within. But regardless of the end, one thing is certain: so-called empty space is not empty. The vacuum is a quantum furnace. On the most minute scales, it boils with virtual particles appearing and vanishing in an instant. They are too fast to capture, yet they leave real physical traces. Imagine a microscope with a resolution far higher than an atomic nucleus, zooming into nothingness at the Planck scale, about 10 to the minus 35 meters. The smooth fabric of space-time will churn like a boiling pot of soup. Geometry shifts between every moment. Virtual particles borrow vacuum energy. The uncertainty principle dictates: the more they take, the faster they repay. Electrons and positrons appear, then annihilate in pairs. The process takes 10 to the minus 21 seconds. More massive virtual particles live for even shorter periods. All particles allowed by quantum field theory take turns playing on this seemingly empty stage of vacuum. It is this invisible quantum furnace that determines how expansion gradually pulls the fabric of space-time. These aren't metaphysical ideas, they leave fingerprints in the lab. The classic case is the Casimir effect. When two metal plates are set very close, the gap can only hold virtual particles with wavelengths shorter than the space. Longer waves cannot enter, but long-wave particles exist outside. This asymmetry generates a pressure that pushes the plates together. This force can be directly measured, as if you've touched quantum vacuum pressure. But what made quantum foam famous in the field of cosmology is that it should contribute to the energy density of the vacuum. When physicists calculated it, the result was absurdly hot. By theoretical accounts, the universe should grow vastly faster. For comparison, the theory is 10 to the 120th power, larger than the actual dark energy. This is one of the most embarrassing failures in theoretical physics history. Either our quantum understanding is missing a crucial piece, or the universe has a mechanism to cancel out most vacuum energy. Solving this vacuum catastrophe might unmask dark energy's true nature. Perhaps that tiny leftover balance is the engine driving expansion. Or perhaps the universe stifles most quantum foam, allowing only a trace to pass. Or else, our calculations are fundamentally wrong. There are even bolder assumptions: the vacuum may be full of hidden fields or extra dimensions, draining the vacuum energy away. Maybe the concept of emptiness itself is an illusion of our limited view. Loop quantum gravity suggests space is woven from discrete loops. String theory sees it as interactions between high-dimensional strings. Whichever side you take, the conclusions converge. Space is not a void background, but a structured medium. Expansion may be stretching this medium, rather than making space from nothing. Even with our limited understanding of the quantum vacuum, the future it implies is stunning. If acceleration keeps increasing, what will happen? An extreme scenario called the Big Rip. In about 22 billion years, dark energy will be so strong that it dismantles all fundamental forces of nature. The universe won't slowly cool over trillions of years, but will collapse rapidly in a short time. The rough countdown is as follows: about 1 billion years before the Big Rip, galaxy clusters are torn apart. About 200 million years before the end, galaxies like the Milky Way will be ripped open. Stars are dragged from gravity's embrace. 30 minutes before the end, the gravity of planetary systems collapses. Earth will be flung away from the sun, and the moon will escape the Earth. In the final minutes, molecular bonds are snapped. Gases dissipate. Oceans boil not because of rising heat, but because molecular distances are stretched until the forces can no longer hold. About 10⁻12 seconds before the end, atoms and nuclei disintegrate. The strong interaction completely surrenders. At the final moment, even distance and time intervals, the metrics used to describe the world, may all lose their meaning. Of course, all of this depends on whether dark energy keeps strengthening. If it remains constant, the Big Rip won't happen. The universe will suppress acceleration, but slowly drift toward the Big Freeze. Existing data supports it being mostly constant, but the precision isn't high enough yet. Future, more refined supernova observations will continue to ask if it's truly changing. If strengthening is confirmed, a specific countdown can be calculated. In 1917, Einstein had just finished general relativity when he ran into a problem. His equations predicted the universe was expanding or contracting. They didn't support a static universe at all. But the mainstream view back then insisted the universe was eternally static. To match this observational impression, he added to his equations a new term, the cosmological constant, lambda. Think of it as energy inherent in the vacuum, like a gentle repulsive force that exactly counteracts gravity, keeping the universe stationary. This patch seemed reasonable, and it actually worked for about a decade, until Hubble used the MT Wilson telescope to measure the distance and velocity of distant galaxies one by one. He found they were generally moving away, and the farther they were, the faster they receded. The universe is not static, but expanding. This was the original prediction, before Einstein added the constant. So he decisively discarded the constant, calling it the biggest blunder of his life. Ironically, decades later, supernova observations in 1998 brought this constant back again. Because we found expansion wasn't uniform, but was accelerating. To drive this acceleration, one needs a uniform energy density that fills all space and generates repulsive gravity. Its effect is identical to the cosmological constant. In other words, if dark energy is the cosmological constant, then Einstein's intuition back then was actually incredibly visionary. Though the reasoning was wrong, the direction was right. Looking closer, the value of vacuum energy is very small, but it's not zero. About 10⁻10 joules per cubic centimeter. This number seems negligible, but when scaled to the volume of the observable universe, it exceeds all matter and the total energy of radiation, directly dominating the universe's late evolution. The problem is, quantum field theory calculations are 10 to the power of 120th times larger than the observed value. This is the famous vacuum catastrophe. Either our understanding of the quantum world is missing a key piece, or nature has a mechanism to cancel out almost all vacuum energy, leaving only a tiny residual. Others have also proposed that dark energy isn't a constant, but a field that changes slowly over time, using dynamic dark energy to bypass the catastrophe. Based on current astronomical data, the simplest cosmological constant model still remains the most fitting explanation. Switching back to Hubble's night of observation, the scientific community was still debating whether spiral nebulae were part of the Milky Way. Hubble used Cepheid variables as yardsticks to measure the distance of these hazy objects to millions of light years or even farther, confirming they were independent galaxies. He then plotted their distances and spectra onto a single chart, and a pattern became immediately obvious. The farther a galaxy is, the faster it recedes. This is what we now call Hubble's law. At first, he thought galaxies were in space, flying apart like fragments from an explosion. But that would put Earth at the center, which clearly violates the Copernican principle. A more accurate explanation is space itself is stretching. Think of galaxies as dots on a balloon. Once the balloon is inflated, every dot sees the others moving away, and the farther they are, the faster they recede. But no single point is the center. Hubble's law became the first solid evidence of cosmic expansion. Its proportionality constant is the Hubble constant, describing how fast the recession is per unit distance. Hubble's original distance calibration confused the types of variable stars. The initial values were too large, estimating the universe's age at only 2 billion years, even younger than the Earth. Later, the scale was corrected, and the age returned to a reasonable range. Yet the linear relationship where greater distance means faster recession remained valid. From neighboring galaxies to the most distant ones, all follow the same curve. This curve not only allowed astronomy to move from 2D sky mapping into an era of measuring the universe in 3D, but also brought a key question to the fore: will the expansion continue forever? The answer depends on how much stuff is inside. Physics has a critical density line that determines if the universe expands forever, or eventually turns back on itself. Intuitively, expansion pushes everything out, while gravity pulls everything back. It's a contest of mass per unit volume. Exceed the critical value, and gravity will ultimately win. Expansion will slow, stop, and reverse into a big crunch. Below the critical value, expansion will always prevail. The world will be diluted to near nothingness, toward the big freeze. If exactly equal to the critical value, expansion speed will approach zero, but never reach it like a ball thrown up just perfectly. It will fly toward infinity, while speed gradually approaches zero. Even more mind-boggling is this razor-edge cosmic density. It looks almost like a vacuum, equating to only 5 hydrogen atoms per cubic meter. Yet it determines the fate of all galaxies, stars, planets, and even our ultimate destiny. For decades, measuring the universe's true density has been seen as the holy grail of cosmology. It sounds simple enough: add up the mass of all matter and divide it by the volume. But execution was difficult, because most of the stuff is invisible. Galaxy rotation curves gave it away. Outer stars rotate too fast. To keep them from flying off, the required gravity needs mass 5 times that of visible stars. So, this invisible mass was given a name: dark matter. It doesn't emit light, nor does it absorb or reflect light. It only affects the visible world by gravity. We rely on its effects on stars, gases, and galaxy clusters to indirectly identify its existence. Even including dark matter, the total density of the universe is only about 30% of the critical density. Based on this account, the universe would expand forever, slowly approaching the big freeze. But dark energy's arrival rewrote the conclusion. Dark energy not only raised the total density, but more importantly, it carries negative pressure. In Einstein's equations, this component pushes space-time to stretch faster. Regardless of how much ordinary matter there is, as long as dark energy is present, expansion will keep accelerating. Combining current observations, our universe is about 27% dark matter, 68% dark energy, and 5% ordinary matter. Considering dark energy's negative pressure, this recipe puts the universe almost exactly at critical density. As if between different geometric fates, a delicate balance was found. This leads back to the flatness problem. Why is the density so close to the critical value? In most evolutionary models, density should have quickly deviated from the critical. Either too high, causing collapse, or too low, causing dispersion. To keep it just right, initial conditions must be precise to infinite decimals. The Big Bang provided a way out. During that period of exponential stretching, any initial curvature was smoothed out. The universe naturally approached critical density. But then a coincidence problem emerged. Why do we live in a window where matter is evenly matched with dark energy? Perhaps it's just the observer selection effect. Only in an era where structures can form, but haven't been completely diluted, can observers like us have the chance to look at the sky and ask questions. Expanding the horizon further, the assumption of a single universe may not hold. In the pathway of eternal inflation, our observable universe is just a small piece of a larger expansion zone. Quantum fluctuations trigger new bubbles elsewhere from time to time. Each universe expands on its own, cooling to form galaxies and planets. Some bubbles have fiercer energy, moving faster; some have denser matter, evolving more slowly. Others have already collapsed, or are even heading toward a big rip. Now, bring in the many worlds of quantum mechanics. Nearly every microscopic branching derives a parallel version of history. So parallel universes are limitless in number. New branches are born every moment. In some branches, you face heat death. In others, you witness a big crunch. And in many more branches, you live on amidst accelerated expansion. Evidence is hard to find, as these universes are causally disconnected. Scientists also try to search the cosmic microwave background, for fingerprints of bubble collisions, but results remain inconclusive. Even so, the multiverse approach still changed how we discuss inflation. For our local space, inflation is overall growth. For a larger structure, it may be just one complex manifestation. Returning to the wings of information, the question becomes more personal. Every thought in your head, every memory, is essentially an arrangement of matter and energy. And the expansion of the universe is slowly diluting these arrangements. It looks like destroying information. Yet physics says information cannot be truly destroyed. The holographic principle offers a perspective. All information within a volume can be encoded on its surrounding boundary. As the universe grows, the boundary's surface area increases. Storage bits increase accordingly. Complexity still has room to stretch. Quantum entanglement joins the fray, keeping particles across vast distances still correlated. It seems to remind us, information is more about relationships than absolute unknowns. The problem is, causal links are severed by expansion. Regions that could communicate will eventually drift apart faster than light. Information is locked in isolated cosmic bubbles, cut off from each other. On a macro scale, cosmic history leaves traces in large structures and the microwave background. On a micro scale, local info is diluted beyond recovery, pushing the lens to the limit of the future. As dark energy pulls space-time further apart, the CMB will redshift until undetectable. Distant galaxies will fall off the edge one by one. New civilizations then looking up may see only a few nearby galaxies, detecting no expansion, nor the afterglow of the Big Bang. They will reach a seemingly simple, yet completely wrong conclusion. The universe is static and eternal. Around 150 billion years from now, dark energy will push most galaxies beyond the world's horizon. Their light stretch longer than the observable universe, disappearing completely from view. To eyes of that era, only our local group remains visible. Meanwhile, the Milky Way, Andromeda, and satellites will merge into one giant elliptical galaxy, floating quietly in the empty void. To them, this cluster of starlight is the whole universe. At the same time, the CMB will also exit the stage. As space continues to stretch, the wavelength of primordial radiation exceeds the observable universe, undetectable by any instrument. Evidence of a cosmic beginning will all be lost. Even the redshift of inflation cannot be measured by a distance. Without seeing distant galaxies, Hubble's law cannot be found, nor can stretching space be proven. Thus, the universe they see will appear static. Based on this reality, future scientists will likely build a different cosmology, claiming that single giant galaxy has existed in the infinite void forever. In a static vacuum, they could hardly imagine a universe once filled with billions of galaxies, drifting apart in expansion. In other words, they will live in a universe stripped of its own history. Furthermore, this loss of perspective will deepen. Future observers will lose clues about early evolution. Nuclear reactions that shaped elements ended billions of years ago. Traces remain only in the oldest stars and are increasingly hard to identify, resulting in an epistemological crisis. Wisdom and technology remain strong, but the universe offers few hints of its nature. The methods remain the same, but with too little evidence, conclusions will go astray. This makes us reflect on our current knowledge. Are we also limited by our era? Have we already missed what only early observers could see? Key info erased by expansion. Civilizations born right after the Big Bang saw sights we can never see. The same analogy extends to the end. As space continues to expand, processes sustaining life will fail. Gas becomes too thin. Gravity can't pull it into clouds. Star formation will cease entirely. Existing stars will fade away. Black holes evaporate via Hawking radiation. Eventually, only sparse particles remain in the void. The universe nears perfect heat death. If observers still exist then, their world will be more deceptive. No stars, no galaxies, no structure, just particles in infinite emptiness. They'll naturally assume the universe was always this dull, unable to imagine past prosperity. From abundance to nothingness, where is the universe expanding to? The question is pushed to extremes. It presupposes a reasonable, but redundant premise, that expansion must have a goal, filling some external space. The truth is simpler. Expansion itself is the reason. It provides a dynamic stage for brief, complex structures to emerge. Galaxies, planets, and life appear because the stage grows. Without expansion, the universe would instantly collapse, or stay eternally monotonous. But this brings us back to the start. In a universe that creates space, generates time, and serves as its own stage. What does expanding to even mean? When you ask where it expands, you assume a pre-existing outside. Like a balloon needs air, or a city needs the countryside. But the universe isn't a balloon. The universe itself is space. When space expands, it doesn't enter an outside realm. It creates the concept of outside. While expanding, no stage exists independent of it. For outside is defined by itself. This isn't a linguistic trap, nor a limit of imagination, but the very structure of reality. Before inflation, inward and outward were meaningless. Expansion creates more space, while generating the rules. For spatial relationships, the universe doesn't expand to a place. It expands by becoming more of itself, rather than invading a non-universe. Following this insight, our understanding of expansion deepens from a mechanical process into a self-bootstrapping reality, pulling itself from nothing to being, from simple to complex. Every inch of new space opens possibilities for matter and energy. The universe doesn't grow for a preset goal. It moves toward a direction that holds infinite potential. We aren't passengers on a ship being taken somewhere. We are part of this process of self-creation. Our consciousness, questions and curiosity are how the universe knows itself. Expansion is not separate from us, because we are part of it. We are space, time, complex patterns of self-organization, able to question our own meaning. From this view, the surface paradox dissolves, and a deeper mystery emerges. If the universe creates space and time, as both stage and audience, existence is stranger than fiction. Perhaps we live in a self-creating, self-sustaining, beginningless and endless, inwardless and outwardless process. The universe expands into itself, making room for infinite possibilities, and for beings like us to find a place. Looking back on this journey, through explosions and dark energy, multiverses and quantum foam, the start and end of time, the truest answer is right before us. As the universe creates more possibilities, we will explain them more clearly. So as we've traveled all this way, we finally realize that what we face has never been just a cold cosmic model. It is both that expanding void, and the very stage of our birth, our thoughts, and our doubts. Just like the question at the start, if the universe truly has rules, is it a product of order or a chaotic accident? Perhaps we won't find the answer for now, but that doesn't matter. Because the process of searching is itself the meaning of human existence. And within the infinity of time, we have only just turned the first page.